In the second part of the review about L'Hopital's rule, we will cover limits of the type infinity minus infinity and 0 times infinity. Both of these cases were explained why are they indeterminate form during our classes. And then we said that we want to bring both of, each of these expression under the form of 0 over 0 in order to be able to use the L'Hopital's rule. Okay, again, I'm going to remind you, we can use the L'Hopital's rule if I have the case of 0 over 0 or infinity over infinity. So let's do the first example. The first example says evaluate the limit of x over x minus 1 minus 1 over ln of x as x approaches to 1 from the right. And right now I'm going to explain why this sign here is important. First, let us discuss on the side what happens with the first factor, x over x minus 1. As x approaches to 1, the numerator goes to a constant, to positive constant 1. Okay? And the denominator goes to 0, so this ratio goes to infinity. Okay? On the other hand, 1 over ln of x, as x approaches to 1, we know that, okay, this is ln of x. As we are approaching 1 from the right, okay, we can see that the graph of this function, right, the values of this function are going closer and closer to 0, which means this denominator goes to 0. 1 divided by something that approaches to 0 is infinity. So both of these cases are going to infinity, and I have infinity minus infinity. Why is it important that we are approaching from 1 from the right? Because if this one, for example, was going to negative infinity, then there is no need to use the L'Hopital's rule. I have negative infinity minus infinity, that would be negative infinity. Or if this one was going to negative infinity, I would have infinity minus negative infinity, which is infinity, plus infinity, which is infinity. So again, because I'm approaching 1 from the right, this difference is going to be infinitely close to 0, but from the right side. This difference is always going to be positive. Very close to 0, but yet positive. So positive divided by positive is positive infinity, and similarly here, positive 1 divided by something that goes to 0, but from the right side is going to be positive infinity, and I have infinity over infinity. Okay, so we have done an example like this in class. What do we have to do in the next step? We have to bring these under common denominator. These two expressions are relatively prime, so the common denominator is just going to be the product of these two terms. So that means that I have to multiply x by ln of x minus I have to multiply 1 by x minus 1. Okay? Now if you send x to 0, well, this term we already know that it's going to go to 0, and 1 minus 1 goes to 0, so 0 minus 0, the whole numerator goes to 0, and here this factor or this factor goes to 0, which means that the whole denominator goes to 0, right? So the denominator goes to 0 and the numerator goes to 0. So we have this case right here, which allows us to use the L'Hopital's rule. So the L'Hopital rule says that if you have a 0 over 0 type of limit, you are allowed to take the derivative of the numerator and the derivative of the denominator, and the limit of the ratio is going to behave the same way as the limit of the ratio of the original expressions. So let's find the derivative. For this one here, we have to use the product rule. Derivative of x is 1 times ln of x, plus x times the derivative of ln of x, which is 1 over x, minus derivative of 1 is 0, derivative of x is 1, so minus 1. In the denominator, again, I have to use the product rule. Derivative of x minus 1 is just 1, so ln of x, plus x minus 1 times the derivative of ln of x, which is 1 over x. So in class I said that it's very important after every application of the L'Hopital's rule to sit down and simplify this expression a little bit. Okay, so at the first step we can cancel these x's. So I have a limit as x approaches to 1 from the right, ln of x plus 1, x divided by x is 1, minus 1, over ln of x plus x minus 1 over x. I will cancel these two constants, okay? And I will bring the denominator under common denominator. So we'll bring this whole thing under denominator x. Okay, I will simplify this expression. So when we divide ln of x by this expression, basically that means that I have to multiply ln of x by this x over x ln of x plus x minus 1. And again, as x goes to 1, ln of 1 is 0. 0 times 1 means the numerator goes to 0. In the denominator I have 1 minus 1, this part here is 0, and ln of 1 is 0, 0 plus 0 is 0. So this allows me to use the L'Hopital's rule one more time, okay? And one more time I have to deal with the product rule here. Derivative of x is 1, so just ln of x plus x times 1 over x. The derivative of the same expression here, plus the derivative of x, which is 1. Now let us simplify this expression a little bit. Cancel x and x in the numerator and the denominator. But now, as you can see, the denominator stays away from 0, which means we're on the safe side, right? As x goes to 1, only this term goes to 0, and this term goes to 0. So I have 1 over 1 plus 1, which is 2. So that's a type of infinity minus infinity. Usually we have to either bring them under common denominator, or the ln function is involved, in which case you have to use the property of the ln function that ln of a minus ln of b is equal to ln of a plus b, and that ratio is 0 over 0 over 0. Okay, and next example is the example of indeterminate form 0 times infinity. So limit as x goes to infinity of x times arctangent of 3x minus pi over 2. So again, we have the inverse trigonometric functions here, which you have to know how do they behave, what's their domain. As x goes to infinity, obviously x goes to infinity, but now the question is what happens with this factor right here. Okay, so the arctangent function has horizontal asymptotes at negative pi over 2 and pi over 2, and its behavior is like this. So as x goes to infinity, obviously arctangent approaches to pi over 2. So if this term goes to pi over 2, this whole factor here is approaching to 0, right? Pi over 2 minus pi over 2. So this one approaches to 0, so indeed we have infinity times 0. And whenever we have infinity times 0, if f goes to infinity and g goes to 0, right, as x goes to some number a, then we will evaluate this limit if you represent this as g of 1 over f, right, will be the same as f times g, or limit of f over 1 over g is going to be the same as the limit of f times g. So now here you have to decide which one is going to go in the denominator, and that for this example should be pretty straightforward, because it's one thing to find the derivative of 1 over x, and it's completely different story when you have to find the derivative of 1 over arctangent of 3x. So I will rewrite this as arctangent of 3x minus pi over 1 over x. Now you should be able to confirm that these two expressions are the same. Okay, they're equivalent. Now let us see whether we are allowed to use the L'Hopital's rule. As x goes to infinity, 1 over x goes to 0. And this factor here, we already talked, pi over 2, sorry. We already talked that it goes to 0, right? Because as x goes to infinity, arctangent of something that goes to infinity approaches to pi over 2. So pi over 2 minus pi over 2 is 0. Okay, that means that we are allowed to use the L'Hopital's rule. So find the derivative of the numerator. Derivative of pi over 2 is 0. Derivative of arctangent of 3x is 1 over 1 plus 3x squared times the derivative of 3x by the chain rule, divided by derivative of 1 over x is derivative of x to the power negative 1, which is negative 1 over x squared. Okay, now because we've used the L'Hopital's rule, we have to simplify this expression a little bit, clear it up. Derivative of 3x is just 3 over 1 plus 9x squared divided by negative 1 over x squared. Okay, let's bring this is going to be the same as 3 over 1 plus 9x squared times the reciprocal of negative 1 over x squared. That's simply negative x squared. And here we have limit of negative 3x squared over 1 plus 9x squared as x goes to infinity. Now here, some of you might think that you should use the L'Hopital's rule one more time because the numerator and the denominator are going to infinity, and that's not wrong. That's correct. As x goes to infinity, the numerator goes to negative infinity, the denominator goes to positive infinity, so you're allowed to use the L'Hopital's rule. But this is one of the easiest limits that we learned in Cal 1 already, and maybe some of you already can recognize that this is going to end up being negative 1 over 3. That comes from negative 3 over 9, and that comes that if I have a ratio of two polynomials, right, and the numerator and the denominator are going to infinity, then that ratio is going to converge to the constant equal to the ratio of the coefficients of the highest exponents, or simply factor of the highest exponent in the denominator, in the numerator is already factored, so that's 1 over x squared plus 9. Cancel the highest exponent and then send x to infinity. As you can see, x appears only here. 1 over something that approaches to infinity is 0, so you're left with negative 3 over 9. Negative 3 over 9 is 1.